Thank you, and thank you for the introduction, Principal. It really is a pleasure to be here tonight and to be joined by so many colleagues, not only from Heriot-Watt, but also from the Building Services Engineering and Public Health Engineering sectors, and from the water community. Thank you. So the title of the lecture then is Water, Wastewater and Opportunity. And if you've had time to read the abstract for this lecture, you'll see that the underpinning theme here is one of water conservation. And as we go through the talk this evening, I'd like to focus on water use and also wastewater disposal. But just to put that in context, we're looking here at water and wastewater disposal in a way that we would use in our daily lives. So in our homes, in our places of work, in public, commercial, and sometimes in industrial buildings. Now that water is supplied by a range of engineered systems, from the very large-scale infrastructure systems right through to the pumps and tanks and pipes that we would see in our home or our place of work. And like many engineered systems, they often tend to be at their best design when you don't notice them. So when these types of systems, when our water and drainage goes wrong, you do tend to notice it quite quickly. So this is something that I'll come back to as we work through the lecture. The other thing to remember is that as we talk about water and water conservation, we should make sure that we identify the link with sanitation and hygiene. And as we talk about consumption levels in the developed world and in the UK, we should also remember the types of statistics that WHO, the World Health Organization, released to us that tell us that something like 750 million people around the world, that's 1 in 10 of the world's population, don't have access to clean water. So it seems only right then that we should scrutinise the level of water that we use. But we should also bear in mind as we work through the lecture that the research that we undertake at Heriot-Watt is really targeted at the internal water and drainage supply for buildings. So the types of output that we have then are targeted towards building codes, design codes, and amending these where necessary, but also addressing the broader water sustainability agenda. So to put this into context then, Waterwise, which is an NGO that promotes water efficiency and water conservation, Waterwise tell us that, I think the website actually says that the average UK person consumes rather than the average UK consumption is, but it tells us that on a daily basis we consume as an individual around 150 litres. And if we put that in the perspective of other countries, we see that in Australia that figure is somewhere between 150 and 200, and the USA somewhere between 300 and 500. And if we look at the other side of the coin, we have China. The per capita consumption is of the order of 100 litres per second. Now, Waterwise also tells us that that's a figure that's been growing every year by 1% since 1930, although my personal perception is that that's probably stabilised. So why is it then, in a country that has a seemingly plentiful supply of water, we have a need for water conservation? Waterwise also tells us that the UK has less available water per person than other European countries, and that we have less rainfall per person than our northern European neighbours. But perhaps surprisingly, when you begin to look at embedded water, so sometimes referred to as a water footprint, but this is the water that's embedded in delivering products to a home, services, food, we see that the consumption rises to almost 3,500 litres per person per day. And then if you make the link to energy and carbon, you can see that we've got up to 25% of household energy bills comes from heating water, and domestic hot water accounts for 5% of greenhouse gas emissions. And you might recall that the then Chief Scientist for the UK government, Professor John Beddington, described this combination of food, water and energy shortage as the perfect storm. So I think that underpins the importance of the work that we do here at Heriot-Watt in water conservation. So we look at how water is used in the home. These pie charts are used quite often to represent this. And I guess if you look across a number of decades, they haven't changed substantially. So we always see that toilet flushing, the WC consumption, has a high percentage. It's always been around 30 to 33%, although reduced recently. The other thing we observe from this is that personal washing, so the bath taps and showers combined, gives us 33%. And over a number of years, a number of decades, you see that this percentage has gradually increased. So between these two factors, personal washing and WC flushing, we actually use quite a lot of water. So why don't we just use less? Particularly with the WC. If you think about how the WC is supplied, the water is treated to potable standard, in other words, to drinking standard. It's supplied through the infrastructure. We then use it to feed the cistern. We use it to flush the appliance, the WC, so we contaminate the water. And then we feed it back into the infrastructure to treat it all over again and recycle. So hugely wasteful in terms of energy, water, and cost. What this rather brightly coloured graph shows is that we have actually targeted water consumption from the WC quite significantly. So the thing to identify from this chart is that if you look at the red dots, first of all, this represents the UK. And what you can see is that before 1940, so around the turn of the century, the UK WC cistern used something of the order of 40 litres per flush, which is a huge amount of water. It was recognised quite quickly that that was entirely unsustainable and the volume had to be reduced. And you can see quite a dramatic change from 1960 onwards and quite a lot of activity from 1980 onwards as well. Now, not all of these recommendations for WC consumption made it to policy or made it to regulation, so some of them are here for information only. But one thing worth noting is that we have quite a significant reduction in WC consumption in the UK post the introduction of the 1999 water fittings regulations. And what you can see here is that consumption value has dropped from 9 litres to this end point here, which is a 6-4 flush. It's a dual flush. So it's now mandatory when you buy a WC that the maximum flush volume would be 6 litre and you would have a 6-4 dual flush. The other thing to note from here are the points in green, which are the USA volumes used in WCs. And again, you can see that they started off particularly high, and then there was some activity that led to a reduction in those consumption values. And that was really driven by a desire in the States to reduce the overall water consumption in properties by around about 25%, and did actually succeed. So if you look at the old consumption volume, what you see is that in imperial terms, we had 3.5 gallon flush that was reduced to a 1.6 gallon flush, and that corresponds to a 6 litre. So pretty much, although not across the board, but pretty much in line with the UK. And the final point is, and I hope they're blue on your screen, but the final point is to look at the blue dots here. They actually show the consumption values for Sweden. And if you look, they actually go as far back as the 1970s. And these are embedded in policy and regulation in Sweden, and shows that we can actually use water consumption of as little as 3 litres in a WC. And that's been done quite successfully over a long number of years. And I think really sets a good example for what we're able to do. So it does beg the question, are we able to still, even at this point, are we able to still use much less water, in particular for the WC, but for the other purposes as well? So that brings us then to the research that we do at Heriot Watt. What are the main drivers behind this? Well, water conservation, we've already discussed. But we also, of course, want to save material, energy, and in some cases space in a building. And the final point is we also want to make sure that we protect health and hygiene. To give you an idea of the scope of what's covered, we usually refer to this as being in building or at the property level. So although we talk about water conservation, and clearly that desire to bring water conservation levels down applies across all buildings, what you'll see is that some of the research that we do and the numerical modelling techniques we have more specifically apply to bigger or more complex buildings, but that conservation message applies across the board. So what do we actually need our water and our drainage systems to do for us? Well, if we look at the top left corner, we see the tap here. We actually need the water to be there at the right flow and the right pressure when and where we need it. For the drainage system, we want to be able to have our drainage system that removes waste, wastewater and waste products, and hopefully removes that as far away from the building as possible and reach the sewer. And for the drainage as well, we need ventilation. So in the middle, we have an appliance trap seal here, and this is a water-based trap seal. And this is the physical barrier between the habitable space and the smells and the disease that reside within the drainage system. And we need that barrier to remain intact. And finally, for rainwater, we want to make sure that we're not prone to flooding. We want to make sure there's no overtopping of gutters, there's no ingress of water into our buildings. And so we've identified then the key functions that we need the systems to provide. What happens then when these systems go wrong? Well, it's quite common that you would have lots of water and drainage problems, but they're usually short-lived. So you may have had a case where you've come across a shower that looks a bit like this, which is really awkward. It usually happens after you've been on a 20-hour flight to the other side of the world and you really need a shower. So clearly flow and pressure problems can arise. The image on the right shows a blockage of some kind. I'm sure most of us will be familiar of something that looks a bit like this and is particularly unpleasant. You may also have had overtopping of your gutter, so this does lead to a number of problems. There can be localised flooding problems, there can be ingress of moisture into the building, and there can also be problems actually around water that gathers around the building that can then penetrate at a later date. Where we have CSOs, combined sewer overflows, what you tend to find is that the environmental damage can be quite severe. So there's a range of cases in which the implications of failure of our systems can be really quite significant. You may have seen images in the news and the press on what happens when we have blockage of drainage systems. These types of images are reasonably common, but still something that we should be able to avoid. This type of blockage will actually cause upstream problems that can be quite severe. And then finally, you have cases where flooding, which is normally combined stormwater and sewer flooding, can be particularly unpleasant. And the consequences of this can really be quite severe. So although this looks messy and we can see that it's a very unpleasant task to clean up after this, there are some real financial, health and social implications of this type of flooding that are particularly unpleasant. In terms of that barrier, the physical barrier between the inside space and the drainage system, it's quite difficult to find an image that signifies bad smell. So this is my best attempt, apologies. But yeah, if your trap goes, then you're exposed to the smell that resides within the drainage system, and it can be unpleasant. In cases where that has happened for a long time, or where there's some air movement that means the air has moved from the system into the building, it can be particularly bad. So that's my attempt at very bad smell. But we shouldn't be too flippant about this, because if that barrier is actually removed, then what you do is you introduce the potential for cross-contamination of viruses and bacteria. And this particular image shows it's not the exact image that was used, but this image is meant to show that we had a case in 2003 where SARS was actually transmitted through a dry appliance trap. And that then led to, I think it was something like 8,000 cases worldwide, 775 deaths across 37 countries. So although the smell is clearly unpleasant, the implications of cross-contamination and disease transmission can be quite severe. So we do need to make sure that we retain that physical barrier between those two spaces. So this is a very simple diagram of the things that we'll cover tonight to try and explain some of the research work that we do. I'd like to focus on 3 different examples. The first will take up the main time in terms of the lecture, and we'll spend most attention we'll look at most attention on this route here, which is the water supply through to the wastewater, and in particular connected to the drainage ventilation system. The second example, which will be shorter, will focus on this rainfall event, and we'll look at the performance of siphonic rainwater systems. And then to finish off, I'd just like to do a bit of a sweep up at the end and pick up on water conservation issues that are driven by appliances that we use, and how we can actually solve some of these problems at the upstream end rather than the downstream end. So we come back to the issue of drainage ventilation. What is it we actually need to do this drainage ventilation system to do? Well, we've said already that what we need a physical separation between the inside space and the drainage network. And that's provided by this trap in the top left. And you'll recognise this tap. It's under your sink, it's under your wash hand basin, it's under the bath. This is the physical protection that we need to make sure that we maintain in order to protect the inside space. But it's also vulnerable to induced siphonage in particular. So where you have a pressure change inside that vertical pipe, that trap is susceptible. In some cases you can actually see it move. 2 or 3 things to remember as we actually progress through the performance issues for these systems. The first is that the airflow inside a drainage ventilation system of this type, so in your vertical stack that you'll recognise from your home, the airflow is of the order of 8 to 15 times the water flow. So for every 1 litre a second of water you have up to 15 litres per second of air. And as that air moves through the system, and generally speaking, it moves from top to bottom, as it moves through the system, it will introduce a pressure regime inside the network that we try to understand so that we can actually counter some of those pressure fluctuations. Now, if you look at design guidance for building drainage systems, we see that the design guidance does actually recognise those pressure changes and does try to account for them. But it accounts for them using steady state methods and using empirical data. So the regulations are generally indicative, but they don't really provide a full picture of system performance. And what we know is that every system is dynamic. It's dynamic because we use appliances in different ways at different times. It's dynamic because the discharge characteristics, sometimes referred to as a hydrograph, will change as the appliance is discharged into the network. And then we have attenuation. We have attenuation of the flow, so the water or the wastewater in the pipes, but also of the air and the air pressure transients as they move through the system. So if we look at how the codes account for these then, what we see here is a very well recognised but steady state pressure response for these systems. So if we work from top to bottom on here, so what we have is an inflow of water in a very simple case in this branch connection here. And so working from top to bottom, what you see is in the top section you have what's called the dry stack friction loss, a very standard loss. So this is only because of air moving through the vertical pipe. And we can calculate this quite readily using Darcy's equation. One of the key points in a system comes when you see the concentrated loss. So this is an increased negative. This is negative direction here. So when you have this increased or this concentrated loss at the connecting branch, what you see is that we have quite a significant decrease in pressure, and that's because the air that tries to move through the system is impeded by the water curtain as it flows from the branch into the main stack. The other aspect that influences that particular profile is the positive pressure, and that's generated at the base of the stack. And again, it's caused by an impediment to air. So again, as the air moves through the vertical pipe and makes the transition to the horizontal, it meets this impediment, which is a water curtain formed at the base. So this is what gives us this very recognisable but steady state profile. In the middle of that section, we have what's called the wet stack suction zone, and that's generated because of the shear between this annular water column and the air that we look at in just a bit more detail in a second. So the other thing to remember here is that as that pressure changes, and as we have changes in the dynamic of the system that's driven by the way that we use our appliances and we discharge into the network, all of these pressures change, and we have the attenuation on top of this. So trying to understand that transient behaviour, the unsteady behaviour, is achieved through developing models, and that's what we've done here at Heriot-Watt. What you see then is you get changes in this profile. And to be able to understand the nature of these changes, we understand the drivers, but to be able to understand the nature of these changes, we develop the numerical model so that we can actually predict the pressure response of the system and then adapt, then put some control strategies in place to make sure that the pressure doesn't exceed the level that would deplete the trap seal. So the fundamentals of the flow then, we have our vertical pipe. And in that vertical pipe, we have what's called annular flow. So in other words, the water doesn't fall in the middle of the pipe. It actually falls as an annulus around the circumference, effectively adheres to the internal surface of the pipe. And standard theory tells us that flow accelerates as it travels down the pipe until it's balanced by the frictional force and we reach terminal velocity and terminal thickness. And in a case like this, where you have approximately or a pipe that would be approximately 100 millimetre diameter, that terminal thickness would be of the order of 5 to 10 millimetres. The key part in all of this is this no-slip interface. This is the interface between that water annulus and the airflow. And this is the part that we're really trying to understand, because this is the driver for the whole system. It's this interface that actually draws the air through the system, generates the pressure change, and means that there is a need for engineers and designers to be able to understand performance and to be able to regulate some of those pressure fluctuations. So to come back to those concentrated losses then, what we've done is we've looked quite closely at the two sets of concentrated losses, one in the branch connection here. So it would be nice to assume that what happens is, as the flow comes in from the branch connection, reaches the main stack, it will head to the other side of the pipe, there will be a swirl component, and it will then come back on itself, and it will travel downwards. So this right-hand diagram is in plan view. So it would be nice to assume that there's a fairly regular path of air, a pathway for air to move through the system, and no real impediment other than the water curtain that's presented here. But these images at the bottom, which are not very clear, they're actually taken from inside an active live drainage pipe. They show that the separation of the water and the air is nowhere as clean as that. So you can see that we have pipe roughnesses, we have a slight angle on the pipe, the water flow is not regular, it's not easy to predict the changes in that water curtain behaviour that then influence the pressure changes. And at the bottom, so you remember this is our other concentrated loss area. This is the other part that we really need to understand. On the left-hand side, we've got this transition from vertical to horizontal. And you see as the water comes down as an annulus and turns the corner, what we've said in this case is there is no separation of the water downflow from the inner pipe radius. And what that means is the water comes down the vertical pipe. As it reaches the bend, it still adheres to the inside surface of the pipe, where it then falls to the bottom and is fed through the horizontal pipe. So there's no impediment, there's no stoppage in this particular case. For the example on the right-hand side, what we do have, though, is we have detachment. So we have what's called a point of separation of the water. So a water curtain is formed. It prevents air moving through the system, and generates, in this case, a positive air pressure transient that is then propagated back through the system. Now that transient has to go somewhere, so we'll come back to this later. Where does the transient go, and how do we account for those changes in pressure? So trying to understand some of these changes then, and how we can account for them through numerical modelling. The image here is Joukowsky, who in 1872 became a professor at the Imperial Technical School in Moscow. And he's quite an interesting character, actually. He actually established the world's first aerodynamic institute, and he mathematically defined the origin of aerodynamic lift and the optimum shape for the aerodynamic shape that we see on aircraft wings. Within the context of water and what we're looking at here, though, he actually also established the water hammer equations. And it's those equations that we use to drive the model and to understand the changes. And one of the key things to remember from this work is that the rate of change of flow condition is the determinant of the potency of the transient. What we also know from this work is that if you actually multiply together some of the factors that indicate how high the pressure change might be, we would multiply fluid density, wave propagation speed, so this is how quickly the change is communicated through the system, by the change in velocity. And if you take something like a WC, which perhaps at its peak has a discharge flow rate of around 2 litres per second, what that translates to is a vertical flow velocity of around 1 metre per second. So you can do this sum in your head. You've got velocity of 1 metre per second that's then stopped by the curtain at the base. So 1 metre per second is stopped. We have a wave propagation speed of the speed of sound, so roughly 320 metres per second, and the density of air is around about 1.2. So you multiply those three things together, you get something of the order of 400 pascals, or roughly 40 millimetres of water gauge. So that gives us then an indication of the level of pressure. They're not huge pressures, but within the context of the system, 40 millimetres of water gauge is sufficient pressure to affect, and in some cases deplete, the appliance trap seal. You'll recognise that that appliance trap seal is of that order in terms of depth. The other thing we have to remember from this work is that pressure transients are also partially reflected and transmitted at pipe junctions, and they're also fully reflected at system boundaries. And if we come back to the case where the transient is generated at the stack base and where does it go, it has to work its way through the system to a point of relief. And some of you might recognise the term pipe period, which is the time taken for the pressure transient to travel to the reflecting boundary and back to the point of inception. And that point is really quite important because that links to the issue of building height, which is why we've got some tall buildings on the slide here. If you imagine, and it's not the case here, but if you imagine that that transient is generated at the stack base, and the point of relief is normally the ventilation point through the roof, so you'll see this system penetrate the building envelope at roof level. This is what you'll see in your own home. If that's the point of relief, then that transient has to travel from all the way from the bottom, the point of inception, to the top and back again before relief is provided. It's not the case in these buildings because these are too tall, but it does bring into play the issue of building height and the importance of building height. So what we've done at Heriot-Watt then is we use our modelling technique, which is a method of characteristics, to be able to understand the system response and to try and regulate, to control these pressures and to work on surge suppression techniques. And as with many models of this type, there are a couple of key messages. The first is that if we look at these characteristic equations, these are the equations that communicate the change through the system and allow us to predict the pressure and the airflow and velocity through the network. So defining the characteristic equations is quite important. Embedded in there, we'll come back to this, embedded in there is the friction factor that is the driver between the water and air interface. So we need to understand that condition. And we also need to understand what we refer to as boundary conditions in any model. So identifying those boundary conditions in the cases of a drainage network, they would be pipe elbows, they would be traps, they would be pipe terminations. Those types of boundary conditions have to be defined and then fed into the model. But once that model's built, we can then look at the way that the system responds in terms of pressure and airflow, and we can begin to control the pressures through the whole network. We have two different types of boundary. One is passive. In other words, the equations are completely independent of time. And the other is active. So in other words, there's a time variance to the definition of that boundary condition. And to give you an example of the types of active boundary that we might have, Fundamentally, these two devices do exactly the same thing, but they tend to be referred to with different terminology. The upper diagram is an air admittance valve, and really is a one-way valve that allows air into the system. Now, what's quite important is if air wasn't allowed into the system at the point it was needed, we need to have lots of additional venting through the network, and that's costly, it's cumbersome, it takes up lots of space. So the air admittance valves allows us to bring air into the system and to relieve some of those pressures. The lower diagram is a waterless trap, so this has no U-bend in the way you might recognise, but instead has a rubber sheath that opens in response to pressure changes or discharge. This also allows air into the system and provides some localised venting. And in this case, what we can do is we can actually look at the pressure loss coefficient and the relationship between that and the local pipe pressure, feed those two items in as active boundary conditions to the model. What that's done then is use of the model has allowed us to develop a product called the PAPA. So we've dealt so far in the lecture only with negative pressures, but recognising that we have positive pressures generated at the stack base. The PAPA was developed at Heriot Watt based on the use or the application of the simulation model and deals with the positive pressures in the system. So the PAPA has inside an expandable bag that changes the way that the wave is transmitted inside the network, decelerates the flow so that we come back to this rate of change issue. So the PAPA provides an alternative airflow path to enable deceleration at a reduced rate, and that's the key point of the PAPA. And you can see here in the lower diagram a case in Hong Kong where some of the PAPA devices are fitted in series in this case to a building that had particular problems with positive pressure generation. So to come back then to the fundamentals and kind of where we are at the minute and still trying to understand what drives the system. If we look at these two characteristic equations, so these are embedded in our method of characteristics technique. What we're trying to understand at the minute is how to define friction factor better. So you might recall the diagram where we had the interface between the water and the air, and that was assumed to be very clean. And you probably have surmised that that interface is not quite as clean as indicated by those diagrams. So what we have is a friction factor that operates at that interface where that interface is not clean at all. And we have some mixing of water and air. It's almost a two-phase flow in the central component of the stack. And trying to understand the surface and the driving factors driven by that, the no-slip interface is really what drives the numerical model. So what we've done is, and these images are taken from the lab in the School of the Built Environment, we've tried to understand how that condition changes. So if you look in what's, I guess, essentially a section view with a high-speed camera and capture some of these images, you might recall from the two diagrams we had side by side that in one case we had no detachment, so the water adhered to the inside pipe surface and was able to flow into the horizontal pipe. And you can see here the white line separates those two areas. So in the bottom section of this image here, you have what's a very turbulent flow as the water moves along the horizontal. But then if you compare that with the right-hand diagram, you have a detachment, you have a formation of a water curtain. Now, this one here doesn't have a particularly large surface area, but you can see that if that surface area was to increase, then potentially you have blockage or impediment that would be complete across the cross-sectional area of that pipe. So similar images, and you can actually see here where the water curtain coverage is much more significant. So on the left, you can see a much higher percentage of coverage here. And then on the right, what we actually have is an image that's been captured where the coverage is complete. So it does look a bit similar to the first one, but I can tell you that there's a layer of water in the upper section of this image and then the turbulent flow in the lower section. So what we're trying to understand is how that water curtain formation is generated, what the drivers behind that are, and how it influences the generation of positive pressure transients in the drainage ventilation system. Now, we did think initially that this was completely flow dependent and flow dependent only. So when you have a lower flow rate, you don't have detachment. When you have a higher flow rate, you do have detachment. And some of the early results might have indicated that that was the case. But once you begin to analyse some of that data more fully, what you see that's not the only driver. There is something else there that up to this point we hadn't quite understood in full. And that's because once we looked at what happened inside the vertical stack, you can see this phenomenon here reasonably clearly actually as we progress towards the bottom of the stack, and you can see these chevrons of water or waves of water as they travel towards the bend at the stack base. So the key thing here, once we had a look, is that what you actually find is this phenomenon which is well recognised, and certainly in civil engineering terms, as roll waves, and that happens in this vertical stack as well. So even although you have a very steady inflow through a branch connection, a very steady downflow inside the vertical pipe, what happens is these roll waves still form. And what we've been able to show is that there is a connection between the formation of these chevrons as they move towards the bottom, connection between these roll waves and the formation of the curtain. So the finding tells us that the link between water flow rate and the formation of the curtain does not act in isolation, that there is this additional component that comes from the roll wave generation in this vertical stack. Once you begin to look at those roll waves in a bit more detail, what you see is that they have parallel paths, but they also have an offset that works vertically and a swirl component, so they do actually move around the stack. And there's a phase shift between the oscillations. So once you begin to analyse the data, you can see a phase shift that suggests we have quite defined roll waves that have, we think, a common frequency of around 4 Hz. And we can see a connection between that frequency in the stack and the frequency of generation of the water curtain that then gives us pressure transients that we would have to be able to control. So I have a video here. I'm hoping it works. This one is not a great view, but hopefully you can see from this video, you can almost see the 4 Hz frequency in the stack here. So please remember, this is a very steady inflow to the pipe. We've eliminated all the factors that might give us some kind of fluctuation, but you can actually see that that's not a clear and steady discharge down that vertical pipe and into the bend at the base. It's quite difficult to see the 4 Hz, but if you look closely enough, you can actually see the variation here. So what do we understand about that phenomenon in stack? Well, we recognise it as being roll waves, and we also know that that roll waves are well recognised, especially, as I say, in civil engineering terms. So roll waves develop traditionally in channels and spillways are the places that we tend to recognise them most, and where there is sufficient slope and limited roughness. And fundamentally what happens is the kinetic waves overtake the dynamic waves, and you have a building of wave parameters that means you have dominant flow depths that emerge in the roll waves, and that's why we think we see them in the vertical stack. But it is very much a natural phenomenon. It's something that once we'd eliminated all of the other factors, we could still identify. And what we're trying to do now is to make quite clear the connection between the roll wave formation and the generation of the positive transient. So some other examples then of where you might observe roll waves. Once you know they exist and once you start to look for them, they are actually quite common. So this is just an inclined roadway, and you can see the formation of roll waves here reasonably clearly. You can also see in the spill wave, they're quite dramatic actually, as where we would probably recognise them most. And in this case here, which is slightly different, I'm just going to pause for a second and actually throw the question to the audience and ask if you recognise these roll waves. Well done. I think the principal was the first one to answer there. I'm not sure what that says. Yes, indeed. There will be a pint waiting for you outside, principal, because of that answer. So, I mean, I guess if you take one thing away from the lecture, recognise the existence of roll waves, whether it's linked to Guinness or not, I'm not quite sure. The mathematical definition of these roll waves is not identical. So what happens in this particular phenomenon here is not identical, but there are similar mathematical characteristics that we can relate to what happens in the vertical stack. So to move then to the stormwater side and to pick up on the rainfall aspects, and again using the same modelling techniques to these types of models to understand system performance. What we have here is a diagram that illustrates the differences between a conventional rainwater and a siphonic rainwater system. So on the left-hand side, we have a conventional system. You'll recognise this from your home. You will have a conventional system fitted in your house, where what happens is the water flows from the roof into the gutter, down the dowpipes, and is connected to an underground network. The driving head there is limited to the depth of water in the gutter. And you can see here that if we had a particularly large building and we needed to move a high volume of water from that surface, it becomes quite cumbersome in terms of the number of vertical pipes that you would have to fit to the building. And also the extent the underground pipe network would have to be quite extensive to accommodate all those down pipes. So siphonic systems have been around probably about 40 years, I think, and are reasonably common. We do find them fitted on large buildings. And the way that they work is that the baffle plate that's fitted inside the outlet means that the air into the outlet is restricted, And when you have a particularly heavy rainfall event, that outlet then becomes submerged, and you have the propagation of full bore flow in what's called the connector pipe, the horizontal pipe, and then downwards through the vertical pipe. And fundamentally what the siphonic system does for you is it means that you can move large volumes of water from a roof surface quite quickly, if that's what you wanted to do. It doesn't necessarily have to be the case that you would want to move it quickly, but siphonic systems do operate very effectively in removing that water from the roof surface. They do have, however, a very limited design scope. So when you design siphonic systems, you'll find that you have to specify a very narrow band of rainfall intensity. And the reason for that is that when you have a flow into the network and into the outlet, that flow through the pipe is balanced against the frictional or the resistance losses from the branches and from the pipe friction itself. So you do tend to find that the design condition for siphonics is quite limited. And what we do is we use the model to try and understand the performance of systems, particularly in the priming phase. So once this pipe operates at full bore flow, what you have is a very steady state condition, and we can understand that quite readily with the application of Bernoulli's equation. But what we don't really understand so much is what happens in the priming phase when you move from what's quite a low rainfall intensity event towards something that would get you close to the design condition. And the types of things that happen, well, you have pulsing, you have, as you move through the priming phase, you have pulsing, you have pockets of air and water that interact with one another, and you have the propagation of transients inside the system. You also have noise and vibration, so when these systems prime, you know they prime, you can actually almost hear them. Although in many cases they don't prime, so the design point can actually often be removed from the case or the design point at which you would want it to be fully primed. So actually if you ask somebody who's responsible for a siphonic system in a building, does the system prime? They'll often say, I don't think so. But you do need it to prime when you reach that specific design intensity. So you need the system, you need to understand how that system works. We also have an ideal case, effectively, where we can predict the performance of the siphonic system, but what we have in practice is quite different. Partly because what we have is an accumulation of detritus in the gutter, builds up around the outlet. So you move the operating point, you actually move the loss coefficient of that outlet. We also need to understand how the performance of systems changes with time as we see changes in rainfall conditions with climate change. So the codes actually tell us how to design siphonic systems as well, but like in the previous example, they specify steady state conditions. So once this system is operating, we can see how the calculations are done, and they're very straightforward, but they don't predict any of that dynamic behaviour. So we use the model to try and understand the response of the system as it moves along the hydrograph curve and towards the peak of flow intensity. And of course, the things you're trying to avoid are gutter overtopping. You want to make sure the outlet is kept clear of blockage so that you don't affect the performance and leading to flooding issues. So I have a video here. It's quite difficult to describe. So I have a video here that shows the installation in the lab. And this is a roof panel with a gutter with a siphonic outlet installed. So it's quite a high flow rate, and you can see that the outlet becomes submerged quite quickly, but really the key point happens underneath with this priming. Now if you watch the priming of the pipe here, you'll see that about 15 seconds into this video, you begin to see the pulse flow, and then it eventually moves to the full bore flow. And modelling this component here and through to the full bore phase is the part that we try to understand. So just about to go full bore, yeah, okay. It's quite difficult to see. It happens on quite a short time scale, that move from the free surface flow through to the priming, but that really is the critical stage in terms of pressure. Siphonic systems are limited by a negative pressure threshold, and we do have to make sure that you don't go beyond that. So in terms of theoretical versus in situ behaviour, we have carried out some monitoring. We have two key sites. Top one on the top left is Ibrox Stadium, where they have a siphonic system that's installed on the front stand. So there's four clearly altogether. The three to the back have conventional systems, but the front stand has a siphonic system. We think because The front facade is a listed building, and so you don't want to have all these downpipes. They have a siphonic system that operates here that has 2 × 7 outlets, so they head in opposite directions on the front stand. So we have this connected so that we get data from the Siphonic system Ibrox, and we can actually look at the performance. I do have to say this one is actually particularly clean. The site is quite clear. There are not very many trees. There are no birds nesting, so the gutter tends to be reasonably clean. It's difficult to identify priming because it's quite a large roof, but the system is also fairly hefty with 14 outlets. The example on the right, other than Chadwick Building, we see the other example is the National Archives of Scotland building, which did have, and it's a long story, but they've now moved to conventional, but did have a siphonic system that we monitored for a long period of time to try and understand the changes in the gutter. So this is a bit, these images that show this in a bit more detail. You can just about see the weather station atop the stairwell here, but hopefully a bit clearer. You can see this here. And then we had pressure transducers monitoring the system, and then we had cameras looking straight into the gutter and monitoring images every 2 minutes to be able to capture the build-up of detritus in the gutter. And because we have the pressure monitoring, you then understand what the change in pressure regime is inside the network. So these are the three images here, 2 on the top and 1 on the left, were captured from that particular site, and actually across a really short time window. So you can see that the accumulation in the gutter happens quite quickly and is quite severe. So you end up with the outlet becomes blocked. It's almost a combination of dust, dirt, water, sludge, bird feathers, a whole combination of things there, but does mean that the outlet blocks quite readily and does actually affect the performance. So what you have here is a shift in the design point. It affects the capacity of the system, and we're able to model that by looking at change in blockage and change in characteristic of the loss coefficient. This one here is a system, I was describing earlier, a system that we actually went and stood on the roof of this building and couldn't find the outlets. We actually had to move the stones to find the outlets. So somebody here that was looking after this building didn't know that those were supposed to be clear. So the key message is the in situ performance can actually be quite different to the design condition. In terms of climate change, we mentioned this briefly. If you've ever looked at the UK SIP site, the climate change site, you can see that from the funding that DEFRA provided, DEFRA was able to, through UK SIP, to generate what's called the UK CPO9 data, climate change data. It's accessible to everybody, and I think is well used in the academic sector as well. And if you've looked at this, what you'll recognise is that's cast across 3 emissions scenarios of low, medium and high, and a number of time periods. There are only a selection here, with probability percentiles against a baseline, well recognised baseline of 1960 to 1991. And in that, from that particular website, what you can do is you can download a weather generator, and that will give you a synthetic rainfall event that allows us to drive the model. What we did was this: we defined a common event that was applicable both to the building system and to the curtilage system, and then identified a failure threshold where you can actually identify the point at which you would not wish to exceed the rainfall intensity. So in most cases, the failure threshold is when the gutter begins to overtop. So what we were able to do then was to identify cases where you would have exceedance of the system. A system has undercapacity under these different emissions scenarios. And this is information that you would share with the building manager so that he or she would then know when to go and take some remedial action. So the final example then is on water consumption itself. So we're now very much at the upstream end and trying to understand how we can actually drive some of this need to reduce water consumption in terms of the actual appliances. And you can see here an example of a hydrograph, and the shape is not changing, but the area under the graph changes as we move to lower volume appliances. And there's a cumulative effect, so it's not just one appliance that has a reduced volume of water. You bring these all together, and what you see is that across the piece, so within a whole building, and in some cases a very large building, the overall consumption of water can be quite significantly reduced. So what does that do then for the performance of systems? Well, do we still have the same drain line capacity in terms of performance of our horizontal drainage? If you reduce the water use, you reduce the depth. Potentially, unless you design correctly, you can reduce the drain line carry. Pumps and pipes, are they still sized properly? We think not. We're just about to embark on a piece of work that looks into why or how we should be designing pumps and pipes for this new cumulative effect of water conservation in our buildings. And one aspect that we're just about to move into is an environmental psychology. So this is about the water use in terms of, or looking at from the perspective of the user here. So as you go into a toilet block and there are a number of cubicles, which door do you go to? Is there some kind of reasoning, the environmental behaviour aspect to this? It's difficult to do this without having a train spotting moment, but there are clearly a number of influencing factors, but it's believed that there is a driving force that says that you will use the same type of area of those cubicles on a consistent basis, as long as the conditions are the same. So in cases where there are particularly dirty cubicles, then you would avoid. But it does call into question whether we have the design, for these bigger systems, do we have the design schemes right? Are there particular appliances that are never used because they have a set of conditions that just mean that people don't want to use them at all? And then, of course, we have the behavioural aspect. It's a bit of an ongoing problem where people throw things into the drains that they're just not supposed to. And we're interested in as well in the behavioural side of this and what that does to the system performance. And then just to look at this from a holistic perspective to try and wrap up, what we're trying to understand collectively, so all of these things put together, is once you start to look at the water flow through a building, and what you're seeing here is one chosen route for water. Once you begin to identify all of these connections together, water reclamation being a key part of that, we could quite easily use water discharged to the drain and not try to use any of the water again. But where you have water reclamation or recycling of some kind, you actually have quite a convoluted flow path here. And we're trying to understand some of these flow paths and to allocate some transfer characteristics to them so that we can identify the time. Residence time is a key identifier, and it leads also to social acceptability in some of these systems. So one of the things that we're currently trying to do with some of the PhD students is to try and understand how these flows work. So to sum up then, if I can just finish with all of the things, collectively the things that we do together as a group and not just myself as an individual, the things that we cover: internal building drainage systems, and we've heard about sanitary appliances and how we use them. Small-scale local drainage and runoff of the curtilage, and so this includes the rainfall and all of the water that we use within that curtilage boundary. Roof drainage, conventional, fairly straightforward, but also siphonic. And water supply, we've talked about water conservation, but there is a loading issue that relates to pumps, and then reclamation of water as well. But all underpinned by numerical modelling. So we use our numerical modelling techniques to identify air pressure transient propagation, free surface pipe flows, solid transport modelling, and the priming of those siphonic systems. And finally, I'd just like to acknowledge the input from the wider team. This is not something that I do alone. There are a team of people, and we've been around for quite a long time now and done quite a lot of work in this. But it's a group of people, a research group that was founded by John Swafield when he came here in 1985. And only this afternoon, and many of you have been here, but only this afternoon we had the inauguration of the John Swafield Building Services Engineering Laboratory. And I'm pleased to see that Jean joined us for that event and joins us here this evening, so thank you, Jean. So all of this work is not mine alone, it's part of a group, it's part of a wider spectrum of activities that we undertake in water supply and drainage, and so I'm grateful to my colleagues as well for their input to this presentation. Thank you.